All right, optimization means finding where some function model has its greatest or smallest value, where we want to make something the most or the least. All right, so types of optimization problems: maximum volume, minimize distance, minimize area, minimize length, minimize cost. And where's my writing? There it is. Minimize cost with an extra I in front. As it once comes off the top of my head. But we want to make something the most or the least. All right, so you're going to write a function and use derivatives to find the maximum or minimum value. So think the optimal size of something or the optimal a number of something. So you maximize or minimize something. All right, so if f is continuous, and this is not in your notes, but the steps are. If f is continuous on the closed interval, then where f has a maximum or minimum must be one of the following. So maximum minimums occur at interior. So these are absolute maximums. And actually, I would like you to write this in your notes. So write this right here. All right, so if f is continuous on a closed interval, then f has a maximum or minimum, and it has to be one of the following. It has to be interior points, where f prime is 0, interior points where f prime does not exist, or endpoints of the function's domain. These are the critical points for the function. Right? So in your notes, how can we evaluate where these critical points? And next to critical points, put f prime of x equals 0. F prime of x is undefined. Right? The endpoints. Those are going to be our critical points. How can they represent maximum values, minimum values, or neither? So what are the tools that we're going to use for this? How did we find maximums and minimums? Think back to curve sketching. How did we find? Did sign chart? What else? What else did we use for any kind of maximum, any kind of minimum?
Could you use extreme value theorem?
Very good. Extreme value theorem, EVT. We got sign charts, we got extreme value theorem. What else can tell us max and minimums? Another tool. This was the last tools we learned to find a maximum minimum. What's that? Second derivative test. There you go. You got them all. Very good. All right, so those are going to be our tools. All right, sign charts, extreme value theorem, second derivative test. The solving is really not any harder than curve sketching. The little bit harder part is going to be the setup. All right, you're really going to have to think what equations could you use to relate your variables. All right, there's still going to be common equations: area, perimeter, volume, surface area, profit. I forgot to put maximize profit on that list before, which we'll learn about at the end. All right, but we may require more than one equation, all right, to take care of all of the constraints that we may have. Right? I mean, it's easy to make something, the maximum volume, just make it infinitely, let's keep making larger, 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 right? But then it costs more and more and more, and you need more and more materials, right? So there's often constraints. You just can't have all the materials you want, and you can't make a container, cost $1 million. No one's going to purchase that. Right? So let's move on. So here is a little picture here. All right, so None of these points is necessarily the location of an extreme value, but they're the only candidates. All right? So, and that is our critical numbers and our endpoints. All right? So, critical number is where f prime, we have f prime of c is 0. Critical number, f prime of c is undefined. Of course, that doesn't mean that the function is undefined, just that the derivative would be undefined, because here's a cusp. And then our endpoints. So if we were looking at this particular diagram, here b would be the maximum. So if we wanted to maximize something, then it would be f of b. That's the max. But what if we wanted to minimize something? Well, then we want f of c, because f of c, that would be the min. Here, if we wanted to maximize something, it would be f of c. That's the max. And here, it would be f of b is the min. And here, we just have endpoints. F of a is the min. F of b is the max. All right? All right, so let's look at our steps here. You didn't have to write this down. If it'd be helpful, so, or if you want to take a picture of it, certainly feel free to do that. By the way, these also get posted to the Schoology site, and if you ever want to print something out, it goes 2 pages per 1 page, because 1 page is too much, and having just one screen on a page is too much. It's too big, and then having 4 of them pages are just too small. All right, so we're going to be dealing with, oh, here, you can ignore this. This is from a little activity. I chose to drop the activity just so that, because it took a whole day, and it wasn't that big a deal. A couple definitions here. And it's not definitions that you need to memorize. Just be able to understand if I say primary equation, secondary equation. So primary equation is an equation or formula for the quantity to be optimized. It's our final equation that we're going to be using. But we usually have to do some things along the way, because like I said, you can make the volume as big as you want if you keep making the package bigger, but then your materials cost more money. So there's usually constraints on costs or how much materials, right? And so you need to take that into consideration, right? So those things you need to take into consideration, those are your secondary equations. Those are your equations, formulas relating the independent variables of the primary equation, right? So we're going to have secondary equations that we use within our primary equation. Right? These secondary equations are actually kind of helpful because they reduce the primary equation to one having a single independent variable before attempting to minimize or maximize it. Right? Because you can't have a whole bunch of variables. Otherwise, then what do? Right? You won't be able to solve. You have to have one variable only. Right? And then you also have to consider your feasible domain. Right? You can't have negative volume. Right? You can't have negative costs. You can't make a enclosure bigger than the materials you have to make it. Right? So we'll also look at those feasible domains. What numbers fit within the problem. Right? These are the steps for optimizing. Right? And these are the ones you have in your notes. All right, so number 1, our diagram here is going to be crucial in helping us set these things up right, because you have lots of information to take in. All right, so number 1, draw a realistic diagram, label all the given information, and select variables for the unknown information. Everything gets a variable. All right, don't worry so much if you have too many variables in the first step. All right, your secondary equations are going to help you minimize those variables. You're going to write a primary equation for the quantity to be maximized or minimized. Generally, it's a formula from geometry, or it's a formula for profit or revenue or cost. You're going to write a secondary equation that can be used to change the primary equations to a single variable. There are ways to relate our many variables that we might have together, so we just have one single independent variable. It'll also take care of the constraints. All right, so next to number 3, it also takes care of constraints.
So what does the red go to? Use sign chart? Is that rule 4?
I think it's in the wrong spot. It is. Then we'll move it to the right spot. I think it like floated around. Also takes care of constraints. You'll determine feasible domain, right? So usually it's like 0 to something, right? It's okay if your upper value is maybe a little beyond the feasible domain, right? You don't have to sit there and calculate every way you could make something, but you want to make sure you're not outside anything that would be possible. You're going to differentiate the equation and then solve for critical values. This is just straight differentiation. It is not implicit differentiation, right? We don't have something that's changing relative to time. We are just finding the maximum, the minimum. We're optimizing. Test the primary equation for critical numbers and endpoints and determine the desired maximum or minimum value depending on the situation. That's where the sign charts went. So we can use our sign charts, right, to help us out. Right. Might also use extreme value theorem. Then you're going to take the second derivative to check your answer. Right? So if you're maximizing something, your second derivative should be negative, right? Because if you want something to be maximum, it should be concave down. And if you're minimize something, your second derivative should be positive because your function should be concave up, right? And then solve for other variables needed to answer the question. So once you solve for your variable, maybe you solve for length, but they want an area, right? Well, you plug it back into whatever equation. Not necessarily a primary equation. It could be a secondary equation. Anything that would answer the question, all right? All right, so example 1, a manufacturer wants to design an open box having a square base and a square area of 108 square inches. What dimensions will produce a box with maximum volume? What is the maximum volume? All right, so we'll draw a box. That's our step 1. There's our box. Now, it's not enough to just have the box. Let's label the box. All right, so, well, it's a square base. All right, so if it's square base, well, then I know that this length, this dimension here and that dimension here have got to be the same. All right, we know that. All right, square base. Sometimes I take little notes here to help me out. We have a surface area of 108 inches. What dimension will produce maximum volume? And what is the maximum volume? So notice we have two different things here. We've got some surface area, but is surface area what we want to maximize or minimize? What is it we want to maximize or minimize? Volume. So volume is going to be the primary equation. That's because that's what you want to maximize. Surface area is going to help us out. All right, so that's going to be our primary. You can also consider, or secondary, excuse me. You can also consider the secondary equation to be your helper equation. Right, that's another way you can think of it. The secondary equation is the helper equation. All right, so we have volume of a box is going to be area of the base times the height. So B is area of the base. All right. So now let's get some of our helper equations in here to help us out. All right? So this is our primary equation. It's not our done equation because it's got lots of problems. It's got 3 variables in there. That's no good. All right? We got to get that down to 1 variable. Actually, the v's no problem. It's the b and the h are the problem. Right? We can't have a b, we can't have an h all in the same equation. We got to get that down to just one variable. First of all, let's represent b. So area of the base, how could we represent area of the base? Let's get that down to something better. So here's our base. How do you find the area of a square?
Isn't it S squared?
What's that?
Is it S squared, like the side?
Yeah, side squared, x squared. I'll put an x there, so because my s's look too much like 5s. So b is going to be x times x, or x squared, right? So we've got b taken care of a little bit. Now we got to deal with the h. So let's use our other equation. So that's our primary equation. Let's grab out our secondary equation. So technically, you can also consider this to be a secondary equation as well. That's one secondary equation. We need another secondary equation. The other secondary equation is the surface area. So equation for surface area for a prism, it's the area of the base, the two bases. Do I need two bases? Open box. All right, so make sure you look to see if this is a closed box or an open box. This is an open box. So not two bases, just one base, plus perimeter times height. All right, that's the formula for surface area. Basically, it's a formula for surface area of anything that's only got one base. All right, so now we know we can take care of the b. The b is x squared, right? And we can take care of the SA. That's 108. So here's how we're using our secondary equations to help us out. So this one's 108 for the surface area equals area of the base is x squared. How am I going to represent perimeter of a square? 4 times x, right? So technically, this is another secondary equation, right? So you can see how you start pulling in other equations to help you out. You're like, okay, well, I can't have p in there. Oh, but wait, I know I can represent p. P is just 4x, right? So you're going to have to, manipulate your equation a little bit. So we got plus 4x, and then times height. There's nothing we can do about height, all right, because we don't know the height. But now, look at, we've got two variables. Right? So now what we want to do is we want to solve for h, because we want to get rid of that variable. And then if we can solve for h, we can take that and plug it back into h here. And then all will be good. All right, so we're just going to subtract the x squared. So we got 108 minus x squared equals 4xh, and then divide by 4x. And I'm actually going to go to a second page on this. All right, so then, because I write too big. So h here, I'm just going to switch the size. H is 108 minus x squared divided by 4x. We're going to take that h and replace it right here. We're going to take that x squared and replace it there, and we're down to one variable. All right, so the bulk of this problem is getting this to be an equation in one variable. The differentiation is pretty easy, and the solving is pretty easy. Right? It's really not much harder than a geometry problem. What's that?
If we're plugging into that equation, wouldn't we still need the volume?
No, because we're maximizing volume.
Okay.
Yeah, we're solving for v. We just want to take care of the x's. All right. So we've got v. We're going to find out what that maximum volume is. We've got v equals. Base is now going to be x squared, right? And then h is going to be that there. So if you think about it, when we were doing curve sketching, right, we had y, and y became dy dx equals, right? That's what v is going to be. It's going to be dv dx, right? And that's going to help. We're going to find it x that way, and then we're going to plug it back in. All right, so x squared times 108 minus x squared over 4x. All right, now we'll simplify this on the other page because I took up too much space. But this is our new primary equation right there. All right, we're in one variable. The v doesn't count. It's like y equals x. All right, the v doesn't count. Everyone got that written down?
Yeah.
Okay. Let's see if we can get this one done. I do have a closing on this, by the way, but it's a very simple one. It's just like how does this compare to curve sketching? So there's no actual solving. And I think I'm going to try to do this as a Nearpod. I think it'll make a nice, pleasant Nearpod. It's not a very participatory one. It does end up being a lot of me, anyhow. So, what was that equation? Yeah, the v equals
X squared times 108 minus x squared over 4x.
minus x squared. 108 minus x squared over
Over 4x.
over 4x. Thank you. All right, we'll simplify. All right, so here let's cancel. And that'll be a 4. This will be an x, and we'll distribute before we take the derivative. So we have v equals 108x, because there's no reason to use a product rule, we didn't need to. Divided by minus, and then we'll divide by 4. 108x minus x cubed. And then let's just divide both of those by 4. Is everyone okay and understands what we did? Right? We multiplied and we just divided everybody by 4. So we make this nothing more than a simple power rule. So this would be 27, right? 27x minus x cubed divided by 4. Now that it's simplified, now we just take the derivative. This is a straight power rule. That's a subtraction sign. It's a wavy subtraction sign. All right, so derivative of v is going to be dv dx, right? Just like dy dx, equals derivative of 27x is 27. Derivative of negative x cubed, 1/4 x cubed is going to be negative 3/4 x squared. All right. What do you think our next step is if we're looking for critical points? Yes. So set dv dx equal to 0. So we have 0 equals 27 minus 3/4 x squared, and now we'll just solve. So 3/4 x squared equals 27. Let's just multiply by 4/3. First, I have to write smaller. Man, I'm taking way too much space. This will cancel. That cancels, of course. I've got x squared equals, that's going to be 36. Take the square root. Technically, there's two answers, plus and minus 6. Which one is outside the feasible domain? Negative 6, right? Negative 6 is outside feasible domain.
Mr. Jagna,
Yeah.
for this week's spell work, would I be able to turn in an after break?
Yes.
Okay.
Let's real quickly, we got one critical point, right? All right, we'll do our sign chart. Let's do this real quick. All right, so I'm going to plug in a 5, and I'm going to plug in a 7. All right? If I'll just move down a bit. The 6 was the 0. If I plug in a 5 over here, I'm going to have 25. I'm going to have something that's less than 25, right? I'm having 3/4 of 25. So it's going to be positive. If I plug in a negative, I'm going to have 49, 3/4 of 49. That's going to be greater than 27. This is going to be a negative. All right, so x equals 6 is a maximum, right? Because we're increasing. Right? I'm not going to even do a decification here. We'll do the second derivative real quick to check it's a maximum. So if I do f double prime, or I guess I should call it dv. If we do d2v dx2, of that number, this is going to be a 0, and this would be a negative 6/8x. All right, if I plug in anything into this, it's going to be negative. All right, if I plug in the 6, dsv over dx squared, I have negative 6 times 6 divided by 8. That's going to be negative 36 divided by 8. That's going to be negative something. Negative 4 point something. What is it, 4.25? Whatever, it's negative, right? So since this is negative, right, this is a maximum. And the only thing we had to do now is plug this into the original equation to find the volume, the maximum volume. All right? Oh, 4.5, thanks. Yeah, I don't know where I came up with 2.5. All right. I'm going to stop the tape real quick and ask you a question. Here.